Hello everybody, welcome back. Today we're going to start Unit 3, which is all about intermolecular forces and properties associated with that. And this unit is one of the most heavily covered units on the AP exam, so it's definitely an important one. So let's get started. So as usual, I always like to start off with a little factoid, and I just find this fascinating, that something could be so loud. That would be like those of us that are on the East Coast. If something occurred out in California, we would hear it on the East Coast. That's just incredible to me. All right, so as I said, Unit 3 is all about intermolecular forces. And we're going to be talking primarily in this unit about liquids and solids. And liquids and solids get lumped together because they have a lot of similar characteristics. For example, they are very, very much incompressible, okay? Whereas gases, for example, are very compressible. You can change the volume of a gas. Liquids and solids, not so much. Okay, so liquids and solids have fairly constant density because you can't change their volume. And these similarities are due to the way that the atoms and molecules are held together. Solids and liquids, the particles are very close to one another. Gaseous atoms and molecules are very far apart. And what this unit is all about is what holds one atom or molecule to another. And that is intermolecular forces. Now, it's really important that we understand the difference between an intermolecular force and an intramolecular force, okay? Intermolecular means a force that exists between one molecule and another one next door. The term intra, that prefix intra, means within. So, for example, these are two water molecules in front of you, okay? If I point to that connection right there, that is not an intermolecular force. That is a covalent bond. That is an intramolecular force or connection. Intermolecular would be a force of attraction existing between one molecule and another, okay? Between molecules, not within them, okay? And if you'll remember from Chem 1, there are 3 types of intermolecular forces that we're going to focus on. London dispersion forces are the weakest, then dipole-dipole attraction, and hydrogen bonding is the strongest type of intermolecular force, so we're going to look at each one independently. Let's start with London dispersion forces. Okay. First and foremost, ladies and gentlemen, all covalent compounds experience London dispersion forces between their molecules. I want to underline this word experience, because what I've gotten in the many years I've been teaching this course is a lot of students will say, this particular molecule has LDFs. Do not use the word has when it comes to intermolecular forces, or these molecules have, because that makes it sound like you think that those forces exist within the molecule, and that is not what we're talking about here. We're talking about forces that exist between molecules. So the word experience is a nice way to get around that. Okay. Now, as we said on the previous slide, London dispersion forces are forces of attraction, but they are the weakest. Okay. If you are dealing with one of our noble gases or any molecule that is nonpolar, and we've talked about what that means. Remember, that means a molecule that doesn't have has a balance of charge throughout its shape. Okay, there's no one side that is more negatively charged or positively charged. It's balanced. Okay, if we're dealing with a noble gas or a nonpolar molecule, London dispersion forces are the only forces, intermolecular forces, that exist between their molecules. Now, what even is a London dispersion force? How can two things that don't have an overall charge experience attraction for one another? Okay, well, let's say that we're looking at the gas that we are all inhaling, O2, okay, which is a nonpolar molecule, okay, it is. However, guys, remember, electrons are not static. Electrons move around. And at any given moment in time, one side of that molecule, just for a moment, might have the electrons sort of leaning to one side, okay? Just for a split second, because electrons can move, maybe the left side of this molecule is slightly more negative, and this side is slightly more positive, just for a moment. That's where that word instantaneous comes in there. If that happens, then what you're going to see in a molecule nearby, because remember, intermolecular forces means between two different molecules. If this end of that molecule is slightly negative, that's going to induce a slight dipole. Dipole just means a polarity, a slight polarity in the molecule next to it. Now, are these molecules completely being made to be polar? No, they're not. They're just slightly polar and only for an instant. So there is a very weak, I know I'm not drawing this very well, a very weak force of attraction between the negative end of that oxygen molecule and the positive end of the other. But it's a very weak force, and it's only for an instant. That's why it's called an instantaneous dipole. So you get this instantaneous dipole, which induces another instantaneous dipole in the molecule next to it, and there is a very weak force of attraction. That is a London dispersion force. Now, some molecules can be induced into that momentary dipole easier than others. And this word, polarizability, is a really important vocabulary word. When you write it down in your notes, underline it, circle it, highlight it, it's important. What determines what makes a molecule more polarizable than another, okay, is the number of total electrons. Okay, if one molecule is simply larger, has a greater molar mass, that's going to mean it also contains a greater number of electrons. It will more easily be polarized, more easily induced into that momentary dipole. Okay, so what that's going to lead to, ladies and gentlemen, if you have, let me actually back up for a second. If a molecule is more polarizable, it's still only going to have London dispersion forces, but those London dispersion forces might just be a little bit stronger than a molecule that is smaller and has fewer electrons. Okay, we're going to look at an example in a minute. So bigger molecules have more electrons And we're going to talk in a minute about how that links to melting and boiling points. On occasion, this is an old-fashioned term, but on occasion you'll see the term van der Waals forces. That just means the same thing as London dispersion forces. Same thing, just two different names. It's kind of an outdated term. All right, let's talk about the second type of intermolecular force, dipole-dipole forces or dipole-dipole attraction. Okay, this is a situation where you have forces of attraction between polar molecules. Okay, let's review, guys, what the word polar means. A molecule that has electrons pulled more to one side than the other. A molecule that's going to have a positive end and a negative end. And opposites attract, ladies and gentlemen. The positive end of this polar molecule will attract to the negative end of one nearby. Okay? Dipole-dipole attraction is a stronger force of attraction than London dispersion forces. Okay? And the more polar the molecule is, okay, and remember we talked about in the previous unit what makes a molecule more or less polar. If electrons are really being pulled to one side of the molecule because there's some element that is very electronegative, that means that's a really polar molecule, and that's also going to lead to stronger dipole-dipole attractions. Okay, so let's look at a practice problem here. And if you want to just pause the video and try and answer it on your own, go for it. Otherwise, I'm going to sort of talk through it. So if you want to try it on your own, pause the video now. But I'm going to go talk this one through. It says the structures of ethane and methanol are shown below. One of these two molecules is a liquid at room temperature, meaning the other one must be something else, probably a gas. Based on their structure and intermolecular forces, predict the molecule which is a liquid at room temperature. Okay, so let's talk this one out. Okay, ethane, that first molecule, if you were to draw that one out, ladies and gentlemen, you would see that it is a completely symmetrical molecule. It is non-polar, which means that it has London dispersion forces only. That is its only force of attraction, intermolecular force of attraction. Methanol is a polar molecule. Okay, now it is covalent, so all covalent molecules have LDFs, London dispersion forces, but because this one is polar, it also has dipole-dipole attraction. I'm just going to write dip-dip. Don't write that on a test or the AP exam, for goodness sake. Okay, so what the question should have said, I should have corrected this. It should have said at the top, one of these two molecules is a liquid and the other is a gas. Look at what we've just written down here. Ethane is held together by LDFs only. Methanol is held together by LDFs and dipole-dipole attraction. The methanol molecules are held more tightly together. There's stronger intermolecular forces, which means methanol is the one that's going to be more likely to be a liquid. Okay, ethane, which is held by LDFs only, those molecules are not held as tightly together, more likely to be a gas. Okay, so this is a great example of a free response question. All right, here's another one. Let's talk this one through though. Don't try this one on your own unless you feel like you're a superstar. It says the table below summarizes some physical properties of chlorine and hydrogen chloride. How can we use our understanding of intermolecular forces to account for the difference in enthalpy of vaporization? Now, you may not know the term enthalpy yet. That means heat. Heat required to boil these molecules. Guys, when you boil something, like when you boil a pot of water on the stove, you are not pulling the molecule water apart. Otherwise, the vapor that comes out of the pot of water on the stove would be hydrogen and oxygen gas, and your kitchen would blow up. All you are doing when you boil or vaporize something is breaking the intermolecular forces. So let's talk about what intermolecular forces do these molecules have. Cl2 is totally nonpolar. So it has LDFs only. Hydrogen chloride is polar. It's also covalent, so it has LDFs and dipole-dipole, which I'm going to write as dip-dip. Again, don't write that on a test. Okay, now, look at the little column that says delta H, the heat required to boil these compounds. Now, this may look backwards. It kind of does at first, because this chart is saying it takes more heat to boil chlorine, which you might not expect because, wait a second, it's only held by LDFs. Wouldn't it be fairly easy to pull those molecules apart from each other? Why is the heat higher? That seems wrong. That seems backwards. Okay, but it isn't. Trust the data. Okay, I want you to look at the question above it. Did you all notice that where it says MW below each molecule, that stands for molecular weight? They have the same molecular weight, the same molar mass. Do these two molecules in front of us, Cl2 and HCl, do they have the same molar mass? No, they do not. And which intermolecular force is affected by the size of the molecule? London dispersion forces. So this is a tricky little question, but this is classic on the AP exam. Even though HCl has two intermolecular forces, and thus you'd think, oh, it must be held more tightly together, it's going to be more difficult to boil, the data says it isn't. The explanation is Cl2 has a greater polarizability because it has more electrons in the molecule. So in this case, this is kind of unusual. Cl2, because it is larger than HCl, is more polarizable. Its London dispersion forces end up being stronger than all of those combined for HCl. That comes up on occasion. Okay, and I'm gonna cover that topic again at the end of this lesson, so stay tuned. All right, let's talk about the third and final type, hydrogen bonding. And I put bonding in quotes because it's not a bond. It's just a force between two molecules, okay, just like the other intermolecular forces. Okay, now hydrogen bonding, guys, is a type of dipole-dipole attraction, but it's more specific. Dipole-dipole, remember, means between the positive end of one molecule and the negative end of its neighbor. Hydrogen bonding is the same sort of thing, but it's between the hydrogen of one molecule and N, O, or F from a neighboring molecule. Why those three? Because they're very electronegative. So hydrogen bonding is simply a type of dipole-dipole attraction, but it's a very strong interaction. Okay? So that picture in front of you is just showing you some different examples of hydrogen bonding. Please notice it is not a bond. It is simply a force existing between two molecules, two different molecules. Okay. Now, one more thing to mention on hydrogen bonding. Obviously, hydrogen has to be present for hydrogen bonding to take place. However, it's even more specific than that. Hydrogen bonding will only occur if hydrogen is chemically bonded to, meaning covalently bonded to, NO or F. Okay, so let's look at these two examples in front of you. All right, the example on the left is covalent, so let me change color here. So it has LDFs. It's polar, so it experiences dipole-dipole attraction. Okay, the one on the right is also covalent, so it will experience LDFs. It's also polar, so it will also experience dipole-dipole attraction. But I'm telling you that one of these molecules experiences hydrogen bonding and the other does not. Okay, maybe you can already guess. The one on the right experiences hydrogen bonding. Why? Because hydrogen is covalently bonded to oxygen. Over on the left-hand side, these hydrogens are not bonded to NO or F. So they do not, this molecule over here does not experience hydrogen bonding. Okay, so we're going to play a little game called, is this hydrogen bonding, yes or no? All right, let's go in order. Let's look at box number 1. It's pointing to a bond between O and H, ladies and gentlemen. That is not hydrogen bonding. That is a covalent bond. Hydrogen bonding, just like the other types of intermolecular forces, are things that exist between molecules, not within. Okay, so number 1 is not. Number 2, is this hydrogen bonding? Yes, it is. It's an intermolecular force, and the hydrogen is bonded to one of those 3 elements. So number 2 works. Okay, come over to the left-hand side. Number 3, is that hydrogen bonding? It might look like it, but it isn't. Let me tell you why. What is the hydrogen physically bonded to? Is that one of NO or F? No, it isn't. So even though number 3 really looks like hydrogen bonding, it isn't. Okay, let's look over number 4 up at the top. Is it hydrogen bonding? Yes, it is. It's between molecules. And again, it's what is the hydrogen bonded to in that interaction? It's bonded to oxygen, so yes, that is an example of hydrogen bonding. Last one, number 5. No, it is not. Okay. Now, I realize that is all part of one molecule, but it is actually, and it's not a chemical bond. It's not a covalent bond between those elements. So it could be, but again, what is the hydrogen bonded to? Nope, not NO or F, so that's out. Okay, so you'll see questions like that on multiple choice a lot. You know, which of the following is an example of hydrogen bonding, something like that. A little bit later on in this unit, we're going to look at another sort of subcategory called ion-dipole forces. When we start talking about things dissolving, okay, in solutions, we're going to see how ions can form forces of attraction between covalent molecules. For example, in this picture in front of you on the left-hand side, if I dissolve table salt, sodium chloride, in a glass of water, the ions are going to separate. Those chloride ions are going to attract to the positive side of the water, the hydrogen side. The sodium ions are going to attract to the oxygen side, the negative side. Okay, but we'll talk about that later on when we get to solutions. Just know that these interactions are stronger than any dipole-dipole attraction. But again, we'll talk more about it later. Okay, so what are some factors in chemistry that can be explained by intermolecular forces? Melting and boiling points, the temperatures at which things melt and boil, are affected by the strength of the IMFs. Because when you melt or boil something, you're not ripping the molecule apart, you're breaking the intermolecular attractions. Surface tension, okay? Maybe you remember that little experiment, maybe you did it in elementary school, where you can get a paper clip to balance, like literally sit on the surface of a glass of water, because the paper clip isn't heavy enough to break the plane of water. Surface tension is impacted by the strength of the IMFs. We already saw a question that involved the amount of heat it takes to vaporize a liquid. Okay. Viscosity is a term that means a resistance to flow. Let me give you an example or two of a very viscous liquid. Things like syrup, honey, motor oil, molasses, thick liquids that don't flow very quickly are very viscous, also tied to the IMFs. Vapor pressure is something we're going to talk about later on. When a liquid vaporizes, how much vapor is there above it and what is its pressure? Volatility, how easily does a liquid evaporate? Okay, for example, when you go and get your flu shots, you know, the nurse puts a little alcohol swab on your arm to clean the area. Alcohol, you probably noticed, it evaporates very quickly. Alcohol is a very volatile liquid. It evaporates quickly. The first four, these properties increase with stronger intermolecular forces. You're going to have higher melting and boiling points, greater surface tension, higher heats of vaporization, thicker liquids, more viscous liquids. Why? Because their molecules are held more tightly together. These two are going to decrease. A liquid that has strong IMFs is not going to evaporate very easily. And so we're not going to get a lot of vapor. We're going to have less vapor pressure. But we'll talk more about that later on. So let me sort of bring this all together now. And then we're going to look at an example and then we'll call it a day. Okay. In general, if you are being asked to compare molecules that are of similar size, similar molecular weight, similar molar mass, then in general, it's London. If it only has LDFs, that's going to be more weakly held together than something that experiences dipole-dipole attraction, which is going to be weaker than something that may also experience hydrogen bonding. However, and the AP exam loves this, if you are comparing molecules that are not the same molar mass, not the same size, then the question gets a little bit trickier. Remember that London dispersion forces are the only one that is impacted by the size of the molecule. So if the molecules are of different size, London dispersion forces can become a more significant factor than dipole-dipole, or even greater than hydrogen bonding. And I'm going to show you an example of what I'm talking about right here. Again, if you want to pause the video and try this one on your own, go for it, but I'm going to talk through it. It says, the table above gives the molecular structure and boiling points of CS2 and COS. Similar molecules, but slightly different. In terms of types and relative strengths of intermolecular forces in each compound, explain why the boiling point of CS2 is higher than that of COS. Okay, well, before we even think about that, let's determine what the intermolecular forces are that are going on with each molecule first. All right, CS2 is a totally symmetrical, balanced molecule. It is totally nonpolar. It has LDFs only. Okay. Now COS is not a symmetrical molecule. It's polar. So it is going to experience LDFs and dipole-dipole attraction. It does not have hydrogen bonding. There's no hydrogens in it, so we don't need to worry about that. But just looking at what intermolecular forces these guys have, you would think that COS would have the higher boiling point because its molecules are experiencing stronger forces of attraction. You'd think it would be harder to pull apart one COS molecule from its neighbor because they're being held very tightly together. There's dipole-dipole attraction. However, I can clearly see that we have to heat up CS2 much more to finally get it to boil. And that indicates to me that even though that seems contradictory, CS2 molecules are held more tightly together. And why might that be? Again, they're not the same size, okay? CS2 is a larger molecule that has more electrons. More electrons, it's more polarizable, which means even though CS2 experiences London dispersion forces only, because of its size and its electron cloud, its polarizability, the London dispersion forces of CS2 end up being stronger than all the intermolecular forces combined of COS. Just let that sink in for a minute. Okay, the AP exam loves questions like that, where the data is contradictory to what you might think, and a lot of times, guys, it is due to the size of the molecule and the polarizability of the molecule. Okay? So I know I've thrown a lot at you, but intermolecular forces, as I said, are one of the most important concepts on the AP exam. So it's important that you have a really firm grasp of this concept and can explain the differences in characteristics between molecules. So I hope you've learned a little something today, and I look forward to seeing you next time.